Hi, my name is Austin Cox and this is homework 4, part A. And here we will be starting with a non-steady state mass balance for a gravity drain tank with inlet flow Q, cross-sectional area AC, and outlet flow defined as alpha times h to the 1/2. And here we will be linearizing this differential equation and then deriving an expression for the transfer function in which we will be relating the height and the flow into the tank. So with our steady state, non-steady state mass balance, we have our cross-sectional area times the differential of height with respect to time is equal to the flow into the tank minus the flow out. And we have defined an alpha. So alpha is going to be equal to the area of the outlet times square root of 2g. And we're just simplifying our expression here to make our derivation a little bit more simple. All right, so next we are going to need to take the Taylor series expansion of our right-hand side. But first I'm going to go ahead and define our deviation variables. And for our deviation variables, we want to define how our variables are deviating from their initial steady state. So we can define those as our h prime, and this is our deviation variable for the height, is going to be h minus h bar. And then for our flow, we can define q prime is equal to our flow minus the q bar. And what the bar is denoting is that is our height and flow at the steady state conditions. So moving forward with our Taylor series expansion, we can go ahead and write that our cross-sectional area times the differential of height with respect to time is equal to the flow into the tank minus our alpha term, and then we will multiply this by the square root of our h bar, and then we will be adding our derivative of the square root of h, and that is going to be 1 over 2 times the square root of h bar. The derivative of our square root of h is going to be multiplied by h minus h bar, and this is just showing the deviation from our steady state. So for our next equation, we're going to want to evaluate our differential while the differential of height with respect to time is equal to 0. So dh dt is going to be equal to 0. So that means our left-hand side is going to be equal to 0. And then this is evaluated at steady state. So our q will turn into q bar, and then we will be again subtracting alpha and then multiplying by the square root of h bar plus 1 over 2 square root h bar, and then this will be multiplied by h bar minus h bar. So you can see on our right here, h bar minus h bar, that is going to be 0. So this term here is equal to 0, and it cancels out. So next, what we need to do is subtract our first equation that we derived using the Taylor series expansion and subtract that from our steady state. So doing so will give us the cross-sectional area times the differential of height with respect to time is going to be equal to q minus q bar minus alpha times 1 over 2 square root of h bar, and then this will be multiplied by h minus h bar. So as you can see here, we have q minus q bar and h minus h bar, and that is what we had defined as our deviation variables. So going ahead and substituting those values in will give us our cross-sectional area dh dt is equal to q prime minus alpha times 1 over 2 square root of h bar, and then this will be multiplied by h prime. So as you can see, the only variable left that is not in terms of our deviation variable is our dh dt. So what we want to do is take the derivative of our h prime. So dh prime dt is going to be equal to, we take the derivative at our steady state, that's a number, so this is going to be 0. So then this will be equal to dh dt. So this will allow us to replace our dh dt with a dh dt prime. So now we have all of our expressions in terms of deviation variables. We now want to take the Laplace transform of our terms with the prime in it. So we'll do that over here. The Laplace transform of dh prime dt is going to be equal to capital H times s, and it's multiplied times s since there is a step change in its magnitude. And then the Laplace transform of q prime is going to be equal to capital Q. And then lastly, the Laplace transform of h prime is going to be equal to capital H. So now we want to take these terms and go ahead and plug it in. So we will have AC times H times S. And while we take the Laplace transform, we also need to take into consideration H prime evaluated at 0. So we will subtract H prime evaluated at 0. And then this is going to be equal to capital Q minus alpha over 2 square root of h bar multiplied by capital H. So now what we want to do is isolate our input and our output terms. But first, our h prime evaluated at 0, this is actually going to be equal to 0. We just need to take that into consideration to ensure that we are at true steady state. So we can move our term here over, and then we will be able to factor out an h from the left side. So that will give us h times our cross-sectional area times s. And then we'll add our alpha over 2 square root of h bar. And then this should be equal to q. And then we can move this here over to the right side. So that'll give us our height is going to be equal to 1 over the cross-sectional area times s plus alpha over 2 square root of h bar. And then lastly times q. So now that we have defined this, we have our transfer function right here. So we can denote that TF. However, we need to fit this into the first order model for a first order transfer function, and that is going to be k over tau s plus 1. So in order to fit that, we will need to fit a common denominator, and we can do that by writing that h is going to be equal to 2 times the square root of h bar over alpha, and this will be over 2 square root of h bar over AC times S times alpha, and then we will add alpha over 2 square root of h bar over alpha over 2 square root of h bar, and then lastly multiply by q. So you can see here, we can make our numerator here equal to k, and then our first term in our denominator, make that equal to tau, and then on the our last term in the denominator, this is going to be equal to 1. So this gives us our height is equal to k over tau s plus 1 times q. And then, so now we need to show that our Q is actually going to be a step change here. So we can do so by saying that H is going to be equal to K over tau S plus 1. And we can define our step change as times A over S. So now what we need to do is take the inverse Laplace transform of this function. And that is going to be denoted as that. So taking the inverse Laplace transform of our function is going to give us our h prime back, and that is going to be equal to a times k, and that is going to be times 1 minus e to the minus t over tau. And then by our deviation variable definition, we know that h prime is equal to h minus h at our steady state. So we can write that as h is going to be equal to move the steady state to the right side. H is equal to h bar plus a times k times 1 minus e to the negative t over tau. And now we can linearly approximate the change in our height using this transfer function. And now we will move into Google Colaboratory and code that out.
Hello, this is homework 4, part A2. In our previous part, we had derived the expression for the transfer function in which we are relating the height and the flow into the tank. Here we will take our tank and actually put some numbers into it. So for our cross-sectional area, we will have 2 meters squared. The drainage flow is going to be 0.5 times the square root of h, where h is the liquid level. We will be simulating the time response of the tank when the initial steady flow rate of 0.5 is increased to 0.55, and we will solve this numerically using scipy.integrate.solve_IVP, and we will be comparing the numerical results against our analytical results obtained by the inverse Laplace transform of our previous parts. So moving into our collaboratory, name this homework 4, part A. So I've already imported our libraries. We have imported numpy as np, scipy.integrate, imported solve IVP, and from plotly.subplots, import make subplots. And moving into our givens, we have set our area to 2, alpha to 0.5, our q naught 0.5, and our q to 0.55. So next, we want to set our h naught is equal to our q naught divided by alpha, and then this value will be squared. And next we want to define our k. Our k here is going to be equal to 2 times np dot square root of our h naught, and we have previously defined this in our previous part, and then this will be divided by our alpha. So next we want to define our tau, and we can define our tau is equal to our area, our cross-sectional area, times k. And then next we want to define our step change, which we had previously defined as a, and this is going to be equal to q minus q naught, and this is just showing our step change for our process. So next we can hit shift enter. Now we want to define our differential that we will be solving. So we will define our right hand side, and we will be accounting for our time, and our dependent variable in this simulation is going to be our height, and our initial value for our height in position 0, this is going to be equal to our vector at position 0. All right, so I'm gonna have to change our h here to v. So this will just define that our first position or height in 0 is going to be equal to h. So next, our dh is going to be equal to q minus alpha, and then this will be multiplied by np dot square root of our height, and then this is going to be all divided by our area to return our dh in a list. We can define that as such. All right, shift enter. All right, so now we want to plug in our differential and our function into our solve IVP. So we'll store that as our result is going to be equal to solve underscore IVP. And function here is the right hand side. And we will be evaluating this from 0 until t end, in which I will still need to define. Our initial guess here is going to be h naught. So next here, our method, we are going to use redow. And then lastly, we want our dense output to be equal to true. So I'll need to define our t end for this. T end is going to be equal to 500 for this simulation. All right, so next we want to define our x-axis for plotting purposes. So we can define t-plot is equal to np dot linspace, and this is just going to be creating an array of values in order for us to plot, and this will be from 0 all the way until t end, and we will go in supporting indexes of 100. H is going to be equal to our result from our initial value problem res, and it's going to be evaluated the solution, and this will be of t-plot, and then we want this being evaluated at 0. And next I want to define our y-axis for our linearized differential equation. So this h is going to be equal to what we had derived in part A1. H is going to be equal to h naught plus a times k, and then this will be multiplied by 1 minus np dot exp for e, and this will be e to our negative t-plot over tau. So now we can go ahead and hit shift enter, and now we want to begin creating your plots. So we can go fig is going to be equal to make subplots, and then next we can go fig dot add scatter, and this will be creating our first plot. So we have our x is going to be equal to t plot, our y here is going to be equal to small h, and then our name is going to be equal to exact, since our small h is going to give us the exact solution. And then similarly for our linearized, we can go fig dot add underscore scatter, and here our x will remain t-plot, however our y in this part will change to big H, and then the name is going to be equal to linearized, and then we can go fig dot update underscore layout to define some heights and widths for our plot. We can make our width here equal to 800 and our height equal to 600. All right, let's check it out. Shift enter. So here we have plotted our exact and our linearized solution. As you can see, they are both very close. However, the exact is reaching the 1.2 and our linearized is starting to approach 1.2 and remaining at our steady state. And we can change our number for our plotting to see how it will react with a shorter simulation. So as you can see, it's still very similar. All right. Thank you for watching. This is homework 1 or homework 4, part A2.